So let's continue our discussion on statistical mechanics. So now we learn about principle of equal a prior probability, as you can see here. Okay, so this principle of equal a prior probability, it forms a fundamental basis of statistical mechanics. Now let's try to understand from an example point of view. Okay, so now let's take a system, okay, which is again the earlier example that I have taken. So it's a box. Okay, now it has got two compartments of, let's say, equal size. Okay, so equal size. Okay, it hasn't become equal, so let me try to make it okay. So let me try to draw a line which divides these two in equal size. Okay, so now I have a ball which I will throw from outside, okay, and it will go at least to any one of these compartments. Let's name these compartments, let's say A and B. So the condition is that, so I take a particle or a ball in this case which I am taking, so this particle will go either of these boxes. So when I throw it, okay, so it will not fall outside the box. Now we know that since these both the compartments are of equal size, okay, so then the probability of getting the ball into the compartment A is equal to the probability of getting the ball into the compartment B, because of both of them are equal size. Since there is only two options, so I will have the probability of ball found in, let's say, compartment 1 will be half. Okay, similarly the compartment B also, this probability will be okay, half and equal. So in this experiment, see, even if I don't do the actual experiment, I know the probability. Okay, that means a prior probability is known to us. Moreover, in this case, this a prior probability which I know for the example that I have taken is equal. Okay, basically if I take this event or particle to exist in, let's say, compartment A or compartment B is equally probable. Okay, now this example can be, or this example can be extended to, in a system, think that you have a particle going into one of the energy states. Okay, so both the energy states which normally do, okay, so the particle going into, so if I have the principle of equal a prior probability is applicable to this system, let's say two-level system, and I have one particle, so there's a equal probability that I can find a particle in any one of these states. Okay, so as we go along we will discuss more on that. So another examples we can talk about, which earlier we have discussed, is coin toss. So in that case as well, see, in a fair coin toss either we can get tail or head, so both of them are equally probable. Okay, and also if it's a fair coin, we know that beforehand the probability of getting a tail is half and probability of getting head is also half. So similarly in other case, let's say when we have this die throwing, okay, in that example as well, so you can think about, when you throw a fair die, so the probability of getting any number, let's say number 3, is 1/6. Beforehand, even if you don't do the experiment, we know the probability, and any one of them, so if you take probability of getting a number 6, number 5, number 3, any one of them will be equal, that is 1/6. So this constitutes the principle of equal a prior probability, and this forms the fundamental basis for this statistical mechanics which we are discussing and will be continue to discuss. Okay, we'll know more about the importance of this principle as we go along. Okay, so next let's discuss about macro state and micro state. So as if you know the basic meaning of this macro and micro, so you can think about the macro state means gives you the macroscopic or the very bird view of the system. Okay, again let's go back to the system we have considered. We have a box. Okay, sorry, so let me take a box. So I have drawn bigger. Okay, and this let me draw a line which divides this. Okay, so let's consider this again. We go back, and then this compartment A and B. So now let's say, so I have these compartments A and B of equal size. Okay, so now let's say I have objects. Okay, three distinguishable objects, which I name it, let's say small a, b and c. Okay, so this distinguishable objects are to be distributed in these two boxes, and as the earlier conditions, if I throw a particle into the box, okay, so it will go any one of the boxes, okay, but it will not go outside the box. Okay, so in that case, so the macrostate gives you the overall or the macroscopic view of the system, or the bird view of the system. So I have three particles. So if I take three of them and also throw it just like that to fall into this any one of the compartments, so what are the possible ways I can get the arrangements or the combinations of the balls within or the in the system? So I can have maybe no ball going into in compartment A. Okay, so there could be 0 balls going into the B, and all three could go to the compartment B. It could be either other way around also, 3 and 0. Okay, or it could be like 2 1. Okay, 1 2 possibly. So these are the distributions, okay, which I will find the system if I have 3 balls which we are trying to distribute in the two compartments of equal size. Okay, so this 0 3, this gives you the macroscopic description of the system. So this 0 3 represents the macro state of the system. Similarly, this 2 1 gives you the another macro state of the system. Okay, so in principle, if you have, let's say, n objects to be distributed in two equal size compartments of a system, okay, so in that case, so here we get the possible ways that I can distribute these three objects in two compartments of equal size. So in that case, I have 4 macro state. So if I have n objects to be distributed in two compartments of equal size, so in that case I will have total number of macro state to be n plus 1. Okay, now how within this 0 3 combination, how does the objects are arranged or are combined to form a group, that gives me the microscopic point of view of the system, and that leads to what is known as microstate. So as a definition is written here, macrostate is a description of the condition of the system from a macroscopic point of view. So it's like a bird view. Okay, so I'm not concerned about which ball is going into which compartment, but like how many of them are there in one compartment, how many in the other. Okay, since I'm throwing all the objects in one shot, so the sum of the objects in compartment A and B should be equal to the total number. Okay, so then let's talk about what is microstate. As I already told you, that microstate is a particular configuration of the individual constituent of the system. So in the earlier examples that we have considered, okay, so let me just redraw the system. Okay, sorry, let me draw the system again. Okay, so I have to draw a line exactly in the middle. Okay, so now, so I have these combinations, right? So this is A and B. So so the particle so I have these 0 3 combinations, let's say. Okay, so A B C objects. So here what happens is that, so I have no particles in compartment A. Okay, all three of these A, B, C are in compartment B. Okay, so I cannot form any other group, meaning I can have A, B, C, B, C, whichever you go, but as a group, there's just one. Okay, so I have only one microscopic description of the system in this case. Okay, so it will get clear as we go along. So now think of the conditions where I have one particle in compartment A and then two particles in, let's say this, in compartment B. So then I can have maybe A here. If A goes into the compartment A, then BC will be here. Okay, see, in earlier case, if you're thinking why the BCA is not another arrangement, see here we are grouping. Okay, so it's not giving any other meaningful condition or situation or the state of the system. Okay, so that's why the BCA is equivalent to ABC, so it's a same group. Okay, so now in this, in 1-2 combination, see here A, if A is in compartment A, then in compartment B you will get BC. So I can have here B and CA probably, yes, or C, then I will have AB. See, these three are different ways or the different groupings of the system, entire system, where in the under the distribution where single particle is there in the compartment A and two particles are there in compartment B. Okay, so these are known as the microstates. So these states or this configuration of the system gives you the microscopic description of the system. So within the macrostate 1 and 2, how the objects are arranged in that macrostate, in microscopically how these objects are arranged, I can find in this way. Okay, so I can have ABC, A in compartment B, B and CA, C and AB. Okay, so macrostate gives you the macroscopic viewpoint of the system, whereas microstate gives you microscopic or from the inner details of the configuration of the system. Okay, so then let's continue our discussion. So let's take a example, okay, where I will consider 4 objects, okay, A, B, C, D, okay, and we wish to distribute them in 2 equal size compartments of a box. Okay, so here again you see I have just extended the earlier example to little bit. I have increased the number of particles. Okay, so this is A, B, C, D. Okay, so again I have this 2 compartments, okay, of equal size, and this follows principle of equal a priori probability, meaning I know that if I take all the 4 particles, it's equally probable of all the particles entering into any one of the compartments. So I call them, so the compartment A and B as we are taking it. Okay, so now here let's see what are the macrostate we will get here. Okay, so macrostate means what? It gives you the macroscopic picture or the bird view of the system. Okay, so we are not concerned about how ABCDs are arranged inside or combined inside. We are looking at, okay, how many particles are there in compartment A and how many are there in B. So in this case, you define ways that I can distribute these 4 particles into 2 compartments of equal size. So in that case, I can have, yes, 0 and 4, I can have 3, 1, I can have 1, 3, I can have 2, 2. Okay, so I can have again 3, 1 I have written. Okay, so I can have this 4 and 0. So there are 5 different ways that I can think about distributing these 4 particles in 2 compartments of equal size. Okay, so here you can think about, so I name them here. So these are different macrostates of the system that we have considered. Okay, these are different macrostates. So 0, 4, as we have written it, the same thing again here, and see we have to remember that this both the compartments of equal size. Okay, so because this has to follow the principle of principle of equal a prior probability. Now if the compartments are unequal size, then this principle will not be applied, because the probability of particle entering into the compartments will change and it will not be equal. Okay, now let us look at the corresponding microstates of the system. Okay, so for this 0, 4, how many microstates we will find? Okay, so see, so for the macrostate 0 and 4, so there is no particle in, or no objects in compartment A, so I can have A, B, C, D in compartment B. So there is, see, the interchange of these particles position will not give me any meaningful arrangement. Okay, so in that, or a meaningful combination, or meaningful, it's the same groups, so that's why number of microstate will be 1. Now in 1-3 distribution, or 1-3 macrostates, okay, so there could be, you know, say A could be in the first compartment, and then correspondingly B, C, D will be in the other B. So if you look at all the combinations, so there will be total 4 number of microstates for this distribution 1 and 3. Similarly 2, so 2 in compartment A and 2 other 2 in compartment B. In that case, all these arrangements will add up to give you 6 microstates. So this A, B, C, D, okay, so I think I have written this twice, so please ignore. Okay, this A, B, in spite of that, there has to be 6, yes, A, B, yes. So even if you ignore this, so there will be 1, 2, 3, 4, 5, 6, okay, yes, CBD, okay, AC, BD, AD, BC, BC, AD, BD, okay, all these things. I think there are 6 the microstate for the macrostate 2 and 2. So similarly you can have 3, 1, okay, so you will get all these combinations and total will give you 4 microstates. Okay, so again you look at, see, from the outside, if we look at the system, so I will have, for this macrostate I can describe the system that there are 3 particles in compartment A and 1 in compartment B. So how, if we go look inside the system, then how they arrange. So there are probable ways there are, so these many ways, of 4 ways I can have the system arranged. Okay, similarly in the last one, we have 4, 0, as we all know, in the 0, 4 is just the interchange of the compartment. So in that case we will get only 1 microstates. Okay, so this gives you total number of microstates. Okay, so in this for this example that we have considered, we will get 4, so so there are 4 particles, so that's why we get 4 plus 1, because 2 compartments are equal size, so I will get 5 microstates. So there is 1, so okay, in earlier thing I think, so there are 5 microstates that we have got. Similarly, so how many microstates we have got? So 5 macrostates. Okay, and then here 1 plus this is 4, 5, so 11 plus 5 is 16 total sorry, okay, 16 total microstates we have got. Okay, total microstates. Okay, so now, is there any way to obtain this total number of microstates, and is there any general formula? Yes, of course. Since there are 2 equal compartments, so the total number of microstates will be given by, and there are n, so if there are n objects or n particles, so the total number of, the general formula for obtaining if we have this distribution of n particles in 2 equal size compartment, will give you 2 to the power n. Okay, so this formula will give you the total number of microstates. So in this case there are n equal to 4, so that's why we get total number of microstates 2 to the power 4 is 16, which is validates our answer. Okay, so let's continue our discussion. Okay, so this number of microstates corresponding to a macrostate is known as thermodynamic probability. Okay, so it's a slightly different from the probability we think about. Okay, so normal probability is always between 0 and 1, but here you will see that, see this on the 4th column, or the rightmost column, there you see this number of microstate for corresponding macrostate 1, 4, 6, in this case 4, 1. So this number of microstate number of microstate for a given macrostate is known as thermodynamic probability. So this is known as thermodynamic probability. Okay, so please kindly make note of that. Okay, so this probability this is a simply number, and in general this is a huge number, because when you talk about real system, let's say gas, okay, so in that case, you know, 1 mole of gas itself, or 1 mole of substance itself contains so many particles, like Avogadro number, right, in the order of 10 to the power 23. Now imagine that many has to be distributed in two equal size two level systems, so two energy states. Think about how many total microstates we will get. It's a huge number. Okay, so that's why, so the thermodynamic probability is defined as the number of microstate corresponding to a given macrostates, and that's known as this. So this is important to remember, is that this probability, this thermodynamic probability, is not same as the probability what we understand. Okay, so and then how do I obtain this thermodynamic probability? No, for the case of, let's say, n particles and two compartments of equal size. Okay, for the case of n particles and two compartments of equal size, if there are, so let me just again read our system. So sorry, so let me just redraw the system. Okay, so equal size, it's saying that. Okay, so now I have in case of n particles, so out of that r particles in a compartment A. Okay, total of, there are n particles, two equal compartments. Okay, and if r particles in compartment A, then it's rest assured that other them, because we are taking n particles and just simply throwing into this box. Okay, so and it's sure that all the balls, if you pick up, it will go any one of the compartments. Okay, in that case, if r is there in the r number of particles are there in compartment A, then n minus r will go into compartment B. Okay, so then total number of meaningful arrangement is given by NCR. Okay, so this corresponds to the number of, so this is like, so this r comma, okay, 9, so this is sorry, so this gives you a definition for a, so the way to write a macrostate. So this is our macrostates, right? This is a distribution. So r in compartment A and n minus r in compartment B. So for this macrostate, how many microstates will be there? That is given by this, or how many ways I can arrange in the meaningful ways I can arrange these particles, n particles. Okay, total n particles in these two compartments, for where I have considered small r to be in the compartment A and n minus r to be in the B. In that case, the total number of microstate is given by n minus c, which is n factorial r factorial and n minus r factorial. So you can calculate this total number of microstate, and which is known as thermodynamic probability. So the thermodynamic probability for a macrostate is the total number of macrostate for that macrostate. Okay, so only for the number of microstate for that macrostate is known as thermodynamic probability. Okay. So the example that we have considered, where in the earlier case, the four particles in two equal size compartments. Let's try to calculate number of microstate for the macrostate 3 and 1. Okay, so now whatever we have learned now to calculate NCR, so for the macrostates 3 and 1, so 3 in compartment, by the way, this thermodynamic probability or the is typically denoted by W or this omega. Okay, so we can think about if we so the W for, so we are trying to calculate for 3 and 4, that is given by n. So there are four number of particles, and r is what? So number of particles or number of objects in compartment A. So n, this is 4 and this is 3. So this is given by 4 factorial divided by 3 factorial. 4 minus 1 is 1 factorial. So I will get here 4 factorial divided by 3 factorial will give you the 4, and divided by 1 is will give you 4. So total will give you 4. So I will have 4 number of microstates for corresponding to 3 1 macrostates, and that's what we obtained here when we learned about this. Okay, so I think this gives you a brief or the basic idea behind microstates, macrostates, and what is thermodynamic probability. So please don't get confused. The probability in the normal sense and the thermodynamic probability, both are not same. Okay, so now let's continue our discussion. So the probability of occurrence of a macrostates. Okay, now that is typically defined as, so the probability of a macrostate or occurrence of a macrostate is given by total number of microstate in that macrostates. There is the thermodynamic probability that we have talked about, and then to the total number of microstates. So this is the ratio of number of microstates in the macrostates divided by total number of microstates of the system. Okay, so now for the case that we have considered, or the example that we have considered, so we have let's say for the 3-1 macrostate. So we know that there are 4 for W. For this case, just we have considered there are 4 number of microstates corresponding to this macrostate, and total number of microstate of the system we have already talked about how to calculate for if we have a system of 2 equal compartments, 2 to the power n is the total number of particles. So I have 16 for the example that we have 16 number of total microstates. So the probability of that macrostate, so the probability of that macrostate which we are considering this W, so W31 will be given by, so total number of microstates in the macrostate is 4 divided by 16, which is 1 by 4. So this is the probability of occurrence of a macrostate. So now you can imagine, see, you can see this on numerator, you see total number of microstates. So that means a macrostate is more probable when you have more number of microstates. Okay, so that gives you, typically, as I have talked about, this number of microstates for a macrostate is quite large in the real system that we have talked about. Okay, so then somehow we can think about the most probable state, okay, which has got more number of microstates. So as we go along, we'll discuss more on this. Okay, so similarly you can find the probability of occurrence of macrostates corresponding to, for a system by just knowing the different microstates.